both of these are, so one thing to keep in mind, this class, we've done a lot with linear algebra and vector spaces. That is most relevant to your quantum mechanics. The vector calculus that we're doing now, most relevant to E&M. So our two examples are going to be electricity and magnetism examples. Just like in linear vector spaces, I tended to point out things relative to quantum mechanics. So one of the most basic problems is the electric field for a point charge. Now, first of all, hopefully, does everyone remember what the electric field of a point charge essentially is in some sort of arbitrary units? I don't care about K's and epsilon naughts. Yeah, but what is it?
Q.
Well, 1Q because it's the electric field. It's Q over R squared, R hat, times whatever constant you need for the units you're in. And that could be K, it might be 4 pi epsilon naught, all sorts of stuff. But how would I write this charge density? How do I write the charge density, rho of R, of a point charge? Delta. And this is one of those things I don't think we emphasize quite enough, is why the delta of R function is so important in physics. We're going to give it a magnitude Q, and then it's delta of R minus R naught if the charge is at some point. Let's say it's at R naught equals 0, then we can just call it Q delta of R. And what that basically says, if you remember how the delta function works, if I integrate this rho of R over some volume, I get Q if R equals 0 is in V, and 0 if R equals 0 is not in V. Right? The delta function tells me, right, it's an infinite spike at some point, in this case R equals 0, and so when I integrate over a delta function, I get 1 if that delta function occurs in my region of integration, and I get 0 otherwise. Now if I wanted to be really careful, because I'm doing three-dimensional integrals, I'll put a little 3 up there to let you know that this is the three-dimensional Dirac delta function, so it's the one that makes sense for volume integrals. Sometimes we write it, sometimes we don't, but most of the time I think people will be careful and write that. So that is the idea. This is important because Gauss's law.
In what direction does the spike go, or does it not really matter?
That doesn't really matter. Yeah, it's just, because if you think about it, it's just like with a function, a scalar function in space, it's a scalar function. It doesn't have a direction. So it's, even though we think of drawing it as a spike, that's left over from when you actually plotted values of functions as a function of x. That spike has no direction. It's just its value. So it's actually going in the fourth dimension, I guess. It's easier for planes. If you think area, you can still draw the spike because you can have the xy plane and then the spike. But if we remember Gauss's law, right, we want the divergence of E to equal, in appropriate units, 4 pi rho of R. So that everything works out the way we expect. If you recall, if I draw the point charge lines coming out, how do I use, this is what we do in freshman physics, how do I use the integral form of Gauss's law to derive the electric field? And I will remind you that the integral form is the integral of E dot dA in appropriate units is 4 pi Q enclosed. Right? How do I use this form of Gauss's law to derive the electric field of a point charge? What do I do? I draw an arbitrary surface, and hopefully now, see, now that you've been spending time with surfaces versus volumes, this is, I think, so Gauss's law, when we teach it to you in freshman physics, is one of the most conceptually hardest steps to make, because we haven't spent a lot of time with these integrals, and we haven't spent a lot of time differentiating between the surface you want to integrate over, the volume enclosed by it, a fake surface versus a real surface, right? So you could imagine this point charge being an actual finite sphere, right? Then we have a real surface sitting there with a real charge density and some volume, and then we have our fake surface, and you're having to distinguish between the two. We did that when we did a bunch of our other integrals earlier, when we were adding up our point charges to get the electric field far away. We had to distinguish between the coordinates within the charge density that we were adding up and the coordinate to the point that we wanted to measure the electric field. So we often have these two completely different physical things we're working with. What do we do once we draw this sphere out here in space? What argument do we make? But by symmetry, E has to be constant and it has to be radial, just because with a point charge there, there's nothing to distinguish direction by. And once you have E constant and radial, then this is an easy integral to do, right? This integral here becomes whatever the constant E is over the integral on the surface. And the integral of the surface is just its surface area, right? So this is E times 4 pi r squared, and we set that equal to 4 pi the charge inside, and we get that E is Q over r squared in some appropriate units. This was how we derived the electric field. Now we know the integral of E dot dA, right, is also what we just said above, the integral over the volume of the divergence of E times dV. That's our integral theorem. Okay. Now, for this to now equal 4 pi Q enclosed, we see that our definition before of the charge density being a delta function is correct, because what we want is to get out of this that del dot E equals 4 pi rho. For that to work, we have to turn the charge enclosed into a volume integral over something. And the right volume integral here is the integral over Q delta of R dV, because that is our charge enclosed in this case. So now we can equate the del dot E with the 4 pi rho, and we see that we have the right idea for rho being a delta function. So this is a case where, if you recall, many times if we wanted to do the integral, we were going from this one over to the divergence integral, because taking the divergence was easier and then doing the volume integral was easier. This is actually a case where the surface integral, because of symmetry, is very easy to do. And that's why we tend to do it as a surface integral, and we do that in freshman physics. There's a reason we do it as the integral first. The other reason is, if we look at this point charge case, if I have the electric field and I want to take the divergence of it, it's non-trivial going in this direction to see that I get a delta function. What I actually get, because almost everywhere in space the divergence is what? What's the value of the divergence of an electric field due to a point charge everywhere in space except where the point charge is? 0. Why is it 0 everywhere? What's a delta function by definition is 0 everywhere except at that one point. Let's do this explicitly. If I want to do this explicitly, the divergence in radial components is, for something that just has a radial component, is 2 over r, the radial component, plus the derivative of the radial component with respect to r. That's something you just have to look up or remember. It's not just dr, because, as I said, the various unit vectors depend on position. So you have to look up, and I'll show you that when we go to the Mathematica later in a later piece of the lecture, but you get these two pieces. Well, let's work those out. 2 over r times e sub r is just 2q over r cubed. And what is d by dr of e sub r? Anyone? If I take the derivative of that with respect to r, what do I get? Not negative 1/3. You're integrating. I get negative 2q over r cubed, which is 0. So the only thing we have to worry about here is its behavior at r equals 0. And the question is, this makes it look like it exactly cancels. It's a very, very subtle point, and I don't have really the time to go through it in super detail, but in fact, the fact that I'm doing a 1 over r times e versus doing a derivative, this will actually at r equals 0 give me the delta function that I need. And so we see from a practical application point of view, even though lots of times we went from here to here to solve our integral, let me ask it this way. Given this example, what is it about this example that shows why this was what we wanted to do in this question as opposed to this integral versus other examples where we saw this and we turned it into this? What was the fundamental difference between the two?
We want to actually solve for E.
So in this case, we wanted to find E. If I don't know E, integrating its divergence is a bit challenging. In the other cases, what did I have? I gave you a vector field, and I wanted the integral. So where you're trying to find a value of something, and you have symmetry, often this form of the integral is the one you're going to use. When you're given the vector field, and you want to compute something about it, often taking the derivative and doing this integral will be the easier one. So that's why we looked at these two different examples.